This is section 7.1, operations on functions. Today we're going to look at four major types of operations: the sum, difference, product, and quotient operations. Starting off with the sum. F plus g of x, which is equal to f of x plus g of x, simply has us take two different functions and add them. The difference, f minus g of x, is equal to f of x minus g of x, so the subtraction of two functions. And then the product, f times g of x, or f of x times g of x. And lastly, quotient, f over g of x, which is equal to f of x over g of x, such that g of x cannot equal 0. For our first example for today, we're going to go ahead and take a look at f plus g of x, f minus g of x, f times g of x, and f over g of x. For the two functions, f of x equals x squared plus 3x minus 4, and g of x equals 3x minus 2. So as they walk us through here on the example, f plus g of x, or f of x plus g of x, we take x squared plus 3x minus 4, add it to 3x minus 2. Because we have like terms with 3x and 3x, but also negative 4 and negative 2, we can go ahead and add 3x and 3x, giving us 6x, negative 4 and negative 2, giving us negative 6. So, and our full answer then should look something like this: x squared plus 6x minus 6. Next, f minus g of x. So f of x minus g of x, we take x squared plus 3x minus 4 minus 3x minus 2. Now in this instance, notice that minus sign does have an impact on how that particular binomial will look. In other words, I'm going to have to distribute that negative. A nice technique to apply here is to change this from a negative to a positive, and then change every sign inside to its opposite. So we can see here, from here we've got 3x minus 3x, which just equals 0. Negative 4 plus 2, which just gives us negative 2. And then x squared does not have a like term. Our final answer, x squared minus 2. Next, f times g of x, or f of x times g of x, looks like this: x squared plus 3x minus 4 times the quantity 3x minus 2. The distributive property will apply here, and the way that this is done, we can take x squared times 3x, but also x squared times negative 2, and they have it here in parentheses, 3x times 3x, 3x times negative 2 again in parentheses, and then lastly negative 4 times again 3x minus 2 in parentheses. Distributing each monomial to the binomial leads to 3x cubed minus 2x squared plus 9x squared minus 6x minus 12x plus 8. Our like terms are as follows: negative 2x squared and 9x squared, which adds to 7x squared, negative 6x and negative 12x, which add to negative 18x, and then the 3x cubed and 8. Well, there's nothing we can do with those, so our final answer is this, and that is the form that I would like us to leave it in. Last but not least, division. So f over g of x, or f of x over g of x, we take x squared plus 3x minus 4, write it all over 3x minus 2, and they indicate here that x cannot equal 2/3. Now, I want to extend our answer and explanation as to why x cannot equal 2/3 in the following way. As it turns out, we all recall that there is one number that we can never divide by, and that number is 0. So what I'm going to go ahead and do is take my denominator and set it not equal to 0. Solve for x. So 3x equals 2, or not equal to 2. Divide by 3. So x does not equal 2/3. So our answer technically has to have that as part of it. It has to indicate that x cannot equal that number. So let's continue taking a look at x squared plus 3x minus 4 and see if we can factor it. So it turns out it is factorable. In other words, two numbers that multiply to -4 and add to +3 are 4 and 1. And as far as the signs that we want here, 4 minus 1 will give us +3. 4 times -1 will give us -4. So all I have to do here is add on to my answer that x cannot equal 2/3, and therefore my final answer in full should really look like this. There's nothing more that can be done with this fraction. There will be problems maybe later where we have common factors in the numerator and denominator, but in this case nothing can cancel or divide out, therefore that is your final. So let's move on to the next set of problems. The exercises here will have us do all 4 operations. The first, and let's say the 5th, will give us good practice. So first, f plus g of x, have us take 8x minus 3 plus 4x plus 5. Okay, now I can actually put both in parentheses, but as it turns out, adding these two will not require any distribution of anything to that second binomial. So I'm going to leave that as is and just add my like terms across. In other words, 8x plus 4x, that's 12x. -3 and 5, that's 2. I'm fully happy with that as a final answer, 12x plus 2. Later on, I may ask us to simplify it a bit further, by maybe factoring out a GCF, but for now, our purposes are fulfilled. F minus g of x, let's take a look. If we go ahead and take 8x minus 3 minus the g of x, 4x plus 5, notice how I've put that in parentheses this time. And this is critical because in the next step, as we saw in the example, I will go ahead and distribute that negative, and noting maybe here plus -4x, -5 to make our lives a little bit simpler. Turning this problem then into 8x minus 4x, which is 4x, and -3 plus a -5, which is -8. I'm going to go ahead and say that's my final and move on. The last two operations we can go ahead and take a look at, f times g of x and f divided by g of x, or f over g of x. Okay. Let's go ahead and do the multiplication. So we have 8x minus 3 times 4x plus 5, noting for both I have parentheses, both binomials, which should call for a FOIL, the FOIL process. If we all recall, first 8x times 4x, 32x squared. Outside 8x times 5, 40x. Inside -3 times 4x, -12x. And then last, -3 times 5, -15. If I continue to simplify, my like terms here are 40x and -12x, which I can add in my next step to positive 28x. Still minus 15. My final answer, 32x squared plus 28x minus 15. F over g of x. Finishing this off, 8x minus 3. All over 4x plus 5. And this is actually a perfectly good final answer, with though us maybe making the note here at the very end that x cannot equal, if we set the denominator equal or not equal, technically, to what we know it can equal, and that's 0. Solving then that x will be, first 4x can't equal -5, and then x cannot equal -5/4. This is a critical final note that has to be made on all of these types of answers. Anytime you are dividing by a variable expression, you have to have that last piece where x cannot equal some number or numbers in some cases. Okay. And let's move on to example 5. This particular problem, again, we're going to go ahead and do all 4 operations with, starting with the addition, then we'll do subtraction, multiplication, and division. Okay. So, addition, x squared minus 1 plus 1 over x plus 1. Now, as we look at this, we have a binomial plus a fraction with a denominator that is a variable expression, which we should probably make the note, even back here, that x cannot equal, if we subtract 1 from the equation, x plus 1 can't equal 0, which I'll do right here. X cannot equal negative 1. So that actually does speak to part of our final answer for this first one. Just adding on to that x squared minus 1 plus 1 over x plus 1 with x not equal to negative 1 as our final. This cannot be simplified, at least right now. We'll leave that as is, noting again x cannot equal negative 1. With the subtraction, very similar, x squared minus 1 minus, again, 1 over x plus 1. And yet again, x cannot equal negative 1. And that is the final answer for the subtraction of those two functions. Multiplication, x squared minus 1 times 1 over x plus 1. For this particular operation, I'm going to take it a step further. I'm going to actually put this in parentheses as well as this. And in the next step, what I'll do is, well, maybe write this over 1. So if I multiply my numerators across, my denominators across, I'll have x squared minus 1 over x plus 1. But I'll take it one step further and start the process of factoring. Okay, because as it turns out, x squared minus 1 we can factor. It's a difference of two squares, which we can factor into x plus 1, x minus 1. And that's quite nice because the x plus 1 in the numerator divides out with the x plus 1 in the denominator, and therefore giving us a final answer of x minus 1. But we need to note that x cannot equal negative 1, just as we did on the last two operations. That is your final answer. Last but not least, the division of the two functions. One thing about division that we need to be very cautious about is that dividing by anything is the same as multiplying by its reciprocal. So I'm going to write the problem as this and then rewrite it as this. Okay, putting these two in parentheses. So again, dividing by this fraction, 1 over x plus 1, is the same as multiplying by its reciprocal, x plus 1 over 1. All we need to do from here is do FOIL. X squared times x is x cubed. X squared times 1 is positive x squared. Negative 1 times x, negative 1 times 1, negative 1. And yes, we still need to write that x cannot equal negative 1 as our final note to our cubic polynomial. Now let's move on to the next page. On the next page, we're going to go ahead and take a look at operations on functions continued, particularly the composition of functions. Suppose f and g are functions such that the range of g is a subset of the domain of f. Then the composite function f of g can be described by the equation f of g of x, or as you see here, f with a parentheses or bracket, g, again, parentheses of x. And I keep using the word of, and that's really what we want to use every time we see that little open circle. And that's what the composition of functions verbally should be stated as, f of g, or f of g of x. Okay, I'll be using this notation more often than the prior notation, as you see here, but it again means the same thing. We're composing one function with another. Let's take a look at example 1. For f equals 1, 2, 3, 3, 2, 4, 4, 1, and g equals 1, 3, 3, 4, 2, 2, 4, 1. Find the composition of f of g and g of f if they exist. So we have ordered pairs in the set notation for f, ordered pairs in the set notation for g, and what we'll go ahead and do is compose f of g and g of f.